But in this video, we're going to go over a few of the answers from the intermolecular forces simulation and just make sure we got what we need to, because I noticed a lot of misclassifications, especially on this last part. So again, the theme that we've seen so far is that the intermolecular forces, so those are attractions between neighboring molecules, those are the things that are going to be responsible for the properties that a substance exhibits. So some properties we'll be looking at or have been looking at are boiling point, melting point, viscosity, vapor pressure, surface tension, things like that. So the stronger attraction between the molecules, the more difficult it's going to be for the particles to separate from one another. So like when we think about what it means to boil a substance, so you're changing from a liquid to a gas. What that means is that the particles get enough energy to become separated from one another. So the stronger those attractions are between the molecules, the harder that is to do. That means we're going to see a higher and higher boiling point, or more and more energy needs to be added in order to overcome those attractions. So when we think about, again, if I have, well, everything is going to have London dispersion forces. So you'll notice that in all my classifications here, and you might have missed this point, and that's fine, but everything technically has London dispersion forces, which I've abbreviated as LDF. And but if we have a nonpolar molecule, so nonpolar means that electrons are equally shared. That means there's no difference in electronegativity, or it might be a symmetrical molecule. So those are the conditions where we have a nonpolar substance, nonpolar molecule. So London dispersion forces are the only forces present if it's nonpolar. If we have a polar molecule, so like we see HCl, right? We look at the electronegativities, look at the difference, 2.2 and 3.0, the difference between that's 0.8. That falls into that polar range. So if it's a polar molecule, we would see dipole-dipole and London dispersion. Again, if you just put dipole-dipole, that's fine. But for nonpolar, so H2, it's two H atoms, two of the same exact kind of atom bonded to each other. They have exactly the same electronegativity. So there's not going to be unequal sharing of electrons, and therefore it's nonpolar. So those H2 molecules only have London dispersion forces. I was noticing on a lot of your papers that you said H2 had hydrogen bonding, and it might seem like an obvious choice because it has the name hydrogen in it, and that H is hydrogen. But hydrogen bonding is specifically going to be a force of attraction that's really, really like a souped up, strong dipole-dipole force occurring between molecules where H is bonded to F, O, or N. So if there are no F, O's, or N's anywhere in the molecule, it cannot have hydrogen bonding acting between neighboring molecules. So H2 is nonpolar, so that should be London dispersion forces. So predicting then which one of these would have a higher boiling point, something with dipole-dipole that's a polar molecule attracting to another polar molecule where those oppositely charged ends are permanent, that's going to have a stronger attraction and therefore a higher boiling point. For 12, so HF and HCl, so both of these molecules are polar, right? So if we look at the electronegativity differences for hydrogen and fluorine, that's going to be a 1.8 difference. H and Cl is 0.8 again. So both are polar, but HF has hydrogen bonding. So again, that's where we have HF, H and F bonded to each other. That's a really, really, like, think about how big that difference is in electronegativity. That's a really, really super polar molecule that's going to stick together even more strongly than the polar molecule HCl. So I didn't rewrite HCl again down here. It's dipole-dipole and LDF, just like the first time. But again, we would predict that HF should have the higher boiling point because it has hydrogen bonding, and that's going to be way, way, way stronger than just the dipole-dipole. And then for our last problem here, number 13, comparing H2 and Cl2, H2 is nonpolar, and we already established that from the question above. And so again, that's going to be only London dispersion forces. Cl2 is nonpolar. That's going to be only London dispersion forces. But we also learned that larger molecules, the more electrons there are to shift around and cause that temporary induced dipole, that is going to have a higher boiling point because that should have a stronger intermolecular force. So they give us the boiling points here, and we can actually see that then. So hydrogen has a boiling point of negative 252.